Well, first of all, I would like to thank Peter Banks and the rest of the arrangement committee for inviting me to this meeting, which I'm sure will be a very memorable meeting. Unfortunately, I think I turned the letters the wrong way in the abstract, but what I mean is incoherent scatter radar, the ultimate instrument for upper polar atmosphere research. And talking about radars, incoherent scatter radars, I cannot avoid to start with Chattanooga. When I was a student in university, it was not a university in Tromsø at the time, at the Auroral Observatory in Tromsø, I learned that Bengt Hultqvist came up with an idea that Scandinavia should build an incoherent scatter radar in Scandinavia somewhere. I got a letter from a friend that was working at UCSD with Jules Fayer and Gene Axford. And he wrote to me that Peter Banks has a position available that is linked to the Chattanooga radar. I applied for the position, and for some reason I got it. I wondered why, and I thought maybe it's because I wrote in my application that I had stayed 1 year in full isolation on Spitsbergen during a winter, watching the aurora. So I thought that maybe since I have been able to survive that, I was qualified to survive some harsh climate in Alaska. So this is Chattanooga. You already have seen a picture of Chattanooga. And also the site itself, the buildings, and inside the control office where everything happened when we were excited by the aurora and the active ionosphere, controlling the whole thing. First, I should repeat a little bit, very simple, about an incoherent scatter, how it works. And when you send out a high power radio wave, it hits the ionosphere, and part of the wave is scattered by the electrons. If they all were random and free to move independently, you would get back a signal that looks like this bell here. But the electrons are not independent. They depend very strongly on the ions. So there are ion acoustic waves up there, and the echo you get back has two shoulders because of the waves that goes back and forth there. And the width of this spectrum tells us about the temperature of the ions. And the difference in the height between the shoulder and the valley there tells us about the ratio between the temperature of the ions and the electrons. The area underneath the spectrum is proportional to the number of electrons present. And if now the whole cloud is moving some way by velocity v, the signal will not be returned at the center frequency, but shifted a little bit. And the shift gives us, this shift gives us the velocity of the cloud, or the plasma that we are looking at. So there's a lot of information in this signal, and the basic work related to incoherent scatter is really to solve the signals and make sensible work out of the very noisy signals that we receive. But we receive very good signals from the Chattanooga. This is the electron density profile that we could measure by a resolution of few kilometers, 4 or 5 kilometers. And these are the electron and ion temperature that we could measure with a much broader height resolution of the order of 45 kilometers or so. But it made meaningful data showing us how the electron and ion temperature changed by height. But we were very interested in the velocities there, and I think this is due to Joe Dupnik, who I worked very close with at UCSD, came up with this scheme that you put the antenna into 3 different directions and measure the velocity, and you combine this observed velocity, and you can derive the ion velocity vector. What you have to assume is that the ionosphere behaves rather uniform while you move the antenna from point to point, and it took typically about 30 minutes to complete one measurement. Well, from these measurements, we derive velocities that look like this, and this I think was what Peter was talking about earlier, that this is a 24-hour run, and the ion velocity is measured at 220 kilometers, and you can see how nicely it's moving toward the east after midnight and toward the west before midnight, reflecting the convection cells that we already have heard about. And in the daytime, it's more or less crossing the polar region. So this is a 24-hour plot at the auroral latitude of Chatanika. Well, remember that I was in Alaska and Peter was there, and he told me that I think you can measure the neutral wind from these measurements because we know the ion velocity, and if we assume that the ion velocity at height of 200, 250 kilometers is in the E cross B direction, we have the electric field there, and since we can measure the ion velocity in the E region, we can derive the neutral wind from a simple solution of the mobility equation, assuming a steady state condition. So the ions are a sort of a tracer of the neutral wind in this part of the ionosphere. So we measure the electric field from the E cross B drift in the F layer. We measure the velocity in the ion velocity in the E layer, and by doing this calculation, knowing a little bit about the model of the ion collision frequency and the gyro frequency, we could derive neutral winds. So this is a measurement of the ion velocity at 106 kilometers that is now used together with the one I showed you for a higher altitude, combined according to this equation I just went through. And the result of this is neutral velocities. There is one day here in April, I think it's July 72, and there is another one in May 72, and this is July 72, I think. So these are some of the neutral velocities we got for 24 hours at these latitudes. And we tried to put all these data we had together and make some kind of an average model. I guess it's rather primitive nowadays, but that's what we had at the time. And we compared this to similar measurements at Milson Hill. So these were our neutral winds derived by Chatanika in the early 1970s. Well, this is just to show you how we can do it today with the iSCAT radar that I will talk a little more about later here. So now we're able to resolve it at many different heights, from 95 kilometers to 119, and we can see how the neutral wind changes by altitude according to these measurements. Yeah, and we are also interested in the current, the ionospheric current, and of course it could be derived this way, but we didn't have a direct measurement of the electron velocity really. Well, if you assume that the magnetic field lines are fully conductive, very conductive, then we could assume that the electron velocities are moving the same way as the ions. The electron velocity is the same all the way down through the E region if you assume that the electric field is conserved. But we can also do it by this, by having the conductivities together with the electric field that now continues the neutral wind that we could derive, and you can then estimate the current by this way. Then we need the conductivities. And to do that, we need some models of the ion neutral and electron neutral collision frequencies and the gyro frequencies. And we could derive these coefficients here and put them into the equations for sigma p and sigma h if you had an electron density. And this is some typical conductivity profile that we could receive or derive. So these are typical measurements from Chattanooga in October 72. And here is an event where you have very strong Hall conductivity and also a strong Peterson conductivity, maximizes here at about 105 kilometers. Here's another profile. It's in the evening, much more quiet. This is midnight. This is, I guess, morning, daytime. And this is in the afternoon. But this certainly shows that there's some activities going on, and then the conductivity then increases. And then if you height integrate those quantities, we can get the daily variation of these conductivity, or conductance, I guess. For this day in May, it's a very nice regular motion. So it's a quiet day, showing the solar behavior of the ionization being reflected in the conductances. This is a day where it was more disturbed. So there's big peaks here, then you have auroral disturbances. And this is, again, an extremely disturbed day. So already from the evening to the morning, you have extremely variations in the conductivity or conductances, which was exciting. But this one is one of the experimental results, I think, that I'm most fond of from Chattanooga. Because here you measure the conductances, and you measure the electric field in the two components, the north-south and the east-west component. So here is a strong southward field and a westward field. And you also can derive the U cross B component, because we could resolve the neutral wind. By combining these things, we could then derive the current, the height integrate ionospheric current, and could compare that with the magnetic fluctuations at Fairbanks College. And this is a fantastic agreement, I think, really proving that the current we were able to estimate from these rather crude measurements with 45 kilometers range gate, we could reproduce the current, the real current that gave us the magnetic fluctuations on the ground. The scale here is of course a little bit arbitrary, but anyhow, the time variation in it is very good agreement, I think. This is actually the Hall component. For the D component, it's more problematic. We also were very interested in the height distribution of the current. And Chuck Reno and SRI were able to derive a multipulse scheme for the Chattanooga radar. So we could measure the ion velocity at the 5-6 kilometers height resolution, and we could derive the currents looking like this. So we can see a strong westward current here, and some tendency for an eastward current here in the afternoon. This is in the morning. And this is then the height integrated current, adding all these together. So at least we got some insight into the height variation of the current. Now I go to the ISCAT facility, which came up many years after Chattanooga, actually about the time Chattanooga moved to Greenland. This was first in operation in 1985. This is the ISCAT antennas that Peter Banks just showed, the VHF antenna and the UHF antenna. This is the heating facility that Max Planck put up in the early 70s, and which ISCAT later took over. And here is a partial reflection radar system. So this large area is full of infrastructure for ionospheric research. Well, ISCAT has the advantage that there is the UHF system had a transmitter and a receiver in Tromsø and a receiver in Kiruna as well as in Sodankela, while the VHF system had all its infrastructure in Tromsø. And from this, the reason for this was that we wanted to measure the three components simultaneously in the same volume where these beams crossed. But in order to get the ion velocity, not only components, it took quite a long time in order to do this kind of integration. So the time we gained by it to resolve the time variation or improve the time variation for compared with Satanica wasn't all that good. And we also did a lot of measurements just by moving this antenna and not using these three altogether. You understand? You know, if we want to measure the electric field at one height and then take ion velocities in the EG region at another height, we have to move these things up and down. And it took 10 minutes maybe to complete the circle. And in that time, the ionosphere would change as it did in Satanica. So it was not much gained really by doing that. But let me repeat a little bit about the idea or the incoherent scatter. You transmit a beam here, and we got the scatter here, and we receive the return signal, the scatter signal within a gate. And the signal that we see is something like this, extremely noisy. So here we need very good computers to get anything meaningful out of it. And that is the big challenge in this, that we need very good signal analysis. But if we do that, we can measure the spectra at different heights. Now with iSCAT, we can do it by a 6 kilometer height resolution compared to the Satanica. That's a big improvement. And you also notice that at the bottom, you have a more like a bell-shaped spectrum. Oh, and up here it looks like the traditional double hump spectra. And out of that, we can derive the electron temperature and the electron density. These are typical data that we can get for several days in a row with the iSCAT facility on the mainland. So there's 3 days in a row, and you see electron temperature increases at day, decreases at night, and here you see effects of auroral particles coming in. And the same is reflected in the electron density, and the ion temperature is not so variable because it's much more linked to the neutral gas. Yeah, this is again the neutral bin. And now I will say a few words about the Svalbard radar, which also was shown by Peter. There are 2 antennas there. One is 32 meters in diameter and one is 40. The one in 40 diameter is fixed up along the magnetic field line. This is fully controllable. So the system now looks like this. This is the old system, and now we have one up there like that. And the nice thing about the Svalbard radar is that it's not the transmitter is not based on klystron. It's based on a transmitter that's composed of many units. So it's not so. The old VHS system, it's very easy to have an error in the klystron, and then the measurement is destroyed. But with the Svalbard radar, if one transmitter fell out, you can still run the system. And it's easier to run it over a longer period. So this is one complete year of radar data from Svalbard, which is a beautiful data set, except that we had some power breaks. One is due to the fact that the power station in Longyearbyen, Svalbard, broke down. But anyhow, these are the kind of data I think that is very worth looking at. And here is another few days of the similar data, these are the electron densities. And if you try to figure out where the maximum is, it looks like this. And if you compare that to model calculations, you see that the measured height is lower than the model height. And if this is compared to what they have derived at Milson Hill, you find that if you change the temperature to take into account this reduction, you can reduce or get a better agreement here. And I guess climate modelers think that if the mesosphere is cooling, as many claims, then it would be also realistic to believe that the F region will cool down. But I think that the the old models probably don't have that kind of quality data that this radar can give to really be a good test. So I think the modelers have to do a lot of work. But now let me come to the last thing here. These plots shows how the spectra can change by height, or can change from time to time. Here, there's a very strong right-hand shoulder, nothing on the left hand. This is the frequency. And here is the left-hand shoulder. Here's the right-hand shoulder all the way up, enhanced, and the left-hand shoulder is gone. Here is a more symmetric spectrum. And this spectra are more plotted out here. This is a common spectrum that we see, double humps and so on, but here, right-hand shoulder turns over to a left-hand shoulder in both cases. This phenomenon is now called NEALS, neutral enhanced acoustic lines. And we wonder, how are they produced? And we have tried to take advantage of the fact that we have two antennas and try to use some interferometry to look at these events in more detail. So what we get out by using these two antennas, this is for the 30-meter antenna, I guess, and this was for the 40. This 32-meter is a 40-meter antenna. You can see the spectra, the skewed spectra here, and by correlation we find out that something happens here, and we try to look at where in the aurora does this occur, and it appears that somewhere within this circle this might occur. So I should now be very quick to go over to the final thing. Of course, if you have a remote station transmit a beam with an antenna like this, they can look from the other antenna across this beam. But what we would like would have a large number of beams that could be looked across like this. And AMISR is one of, or is the only one, I guess, a radar in the auroral zone that can do this now. But in ISCAT, we are planning to build a radar that can have several remote stations, as well as a transmitter, of course, and cross a lot of beams. And we can hope to measure in this volume at the same time with many points. So it's a kind of a volumetric ionospheric imaging. And this is the concept that we are working on. It's accepted as a European strategy for research infrastructure. It means S3. So EU has supported this within a limit between 60 and 250 million euro. The proposal that's been sent in now is 135 million euro. It's pretty well supported by, this is a concept for where the transmitter should be, either here or here in Tromsø region or here in the inside Tromsø, and receiving stations at different places to have different spatial resolutions. Oh, sorry, now something happened here. I don't know. But this is the ISCAT 3D, we call it, and it's one of the 42 S3 projects. Now it's an estimate of 135 million euro. Norway and Sweden have strongly supported this. They haven't said that we will have 30 million, but that's what we are looking for. Finnish contribution are working on putting this system on the roadmap. UK is doing the same thing, and Japan is working on these plans. And then we hope to have contributions from some other countries. Is it possible to take this away, or I guess I don't need? So I think I will end here, and thank you for listening.
Okay, we have time for a few questions. Any hands? Any takers? Yes, Peter.
So what is the physical model? Excuse me. What is the physical model for this, the enhancements? Are those field-aligned currents of different directions and crossing?
Yes, that's what is most strongly discussed, the field-aligned current.
And those vary with altitude. It looked like that it would start at a high altitude, and the cross field currents would move down, maybe with some type of turbulence.
Yeah. Well, but hopefully we will get a better clue on it when the new system works.
Thank you.